Okay, so we have what is called a density curve. And a density curve has certain properties. It is always above or on the horizontal axis, number one. A density curve also has an area of exactly 1 underneath it, okay? And a density curve can come in several different shapes. A density curve describes the overall pattern of a distribution. The areas under the curve represent the proportion of the observations that fall in a particular range. It is also an approximation that is easy to use and often accurate enough for practical use. Density curves have a few drawbacks, okay? They don't necessarily describe outliers, and you can see from my curve here, is not exactly real world data at all times, but it can be a good approximation. So, median of the density curve is the point that divides the area under the curve in half. Okay, if I have an area of exactly 1, then the median is going to be half of that area. The mean is going to be the balance point. So if the distribution here were made of solid material, the green line here is going to be the median, and the mean is going to be the point where it balances there. And those two things may not necessarily be the same if the distribution is skewed. So we have here a little bit about notation. Okay, you've already seen this notation. We have X bar, which is the mean, and we have S, which is the sample. This is data that comes from the sample within a population. Okay, so we have here Greek letter. Anybody know this? Mu. Mu is the mean in a population, and this Greek letter is sigma, which is the standard deviation in a population. So mu and sigma come from a population, X bar and S come from a sample, which we will talk about a lot more as we go forward in the course. But for right now, for example, if I'm talking about the population of students at McKinney High, and I take a random sample of 100 students from all of the students, okay? The overall student body is the population. The random sample is the part that comes out of the population there. So we always use X bar and S when we're talking about, we use mu and sigma when we're talking about the overall population. Yeah.
Did you say the green triangle?
Say what?
The green triangle.
The green line there is the median, and the blue triangle there is the median. Okay, so we have what is called a normal distribution, which is fairly important in stats. If we use an idealized distribution, a model distribution close to that ideal, we're talking about a normal distribution. So any normal distribution we can describe with two things, okay? The notation is like this. I have N standing for normal distribution, and then I have mu, and I have sigma, okay? written like that. The mean of a normal distribution is at the center of the symmetric normal curve, and the standard deviation is the distance center to the change of curvature points on either side. So for example, there's a lot of things in life that are normally distributed. For example, we might have a mean of 100 and a standard deviation of 15. This might represent an IQ test, for example. Okay, an IQ test, they write them so that the average on that test is 100 deviation of 15. The SAT is another normal distribution. The test is written so that average is 500 with a standard deviation of 100. Let's talk about certain characteristics of the normal distribution. They have the same shape. They are always symmetric. They are single peak. And bell curve. Bell shaped. Any specific normal curve is completely described by giving two things: the mean, mu, and standard deviation. Which is sigma. Okay. So the mean is the curve, and it's as the mean. Why are they the same? Because specifically the normal distribution is symmetric, therefore the mean and the median will be the same. And the standard deviation controls the spread. Larger standard deviations are more spread out. All right. And so here we have two normal distributions, here and here. My mu, the mean, is at the center. Which one of these two distributions has a larger standard deviation? It's this one, right? Because it is wider and more spread out. And so sigma going to occur at the point which is concavity. All right, and that is called, who should I pick on? My calculus student from last year. That's called what, Alicia? Put you on the spot. You want help? Anybody? It's called a point of inflection. And a point of inflection is where bad calculus. What changes? Point of inflection is where the second, right? It's where the second derivative is the zero or undefined and changes signs. Okay. So this is my point of inflection. That little calculus tangent there. Point of inflection is where the concavity. So if I'm here up at the top of the mountain, the house is skiing, right? This curve is concave down. Down here, it is concave up. So at some point it changed concave. Opens down, opens up. The point at which it changes concavity is called a point of inflection. And that is where sigma is located in the normal distribution. So the point of inflection there and a point of inflection there. There's a change in where the first standard deviation sigma is located. So all normal distributions have this property, yeah, go ahead.
Actual change.
Sure, I can. It's in the grand scheme of things, it's important, okay? So in the curve here, it opens down. And if I down here, this opens up. So at some point it's, okay? Where did it happen? Right in there. Okay, there's just, I'm estimating right here. So this is saying the first deviation is point is constant. But that's that important in the grand scheme. 68.97 sheet, all right, should have modeled this somewhat, okay. 8% one standard deviation. 90 fall within two deviations of, and 99.7 the data for standard. This works for distribution approximately 99 within. Do you have a question? According to this, are approximately normally distributed with a mean of 149 and a standard deviation of 8. Sketch this distribution, labeling the mean and points 1, 2, and 3 standard deviations from the mean. Okay, so here we go. My mean is going to be there in the center, and they tell me that the mean is 149 centimeters. All right, so let's go out some point, let's say right about there. I'm estimating that's going to be 1 standard deviation above the mean. And over here, that's going to be -1 standard deviations. Okay, so if I take 149 and add 8 to it, that gives me 157. So this is going to be 157 centimeters. And if I subtract, that will be 141. Okay, that's one standard deviation. So what percentage of the data is between the mean and one positive standard deviation?
30, sorry.
Okay, it's 68 total within one. So this would be 34% and 34%. Okay, so now I go out to 2 sigma. And so if I add 8 to the 157, that gives me 165. And I'm going to go out to 2 sigma, -2 sigma over here, and subtract 1. Subtract 1. So subtract 8. Okay, so give me 133. Let me extend this out a little bit. We'll go to 3 sigma. And -3 sigma. Okay, so this is going to be 125. And let's see, what's that, 173? And I'm going to go ahead and fill in the percentages, right? So there's 95% between 2 standard deviations. All right, so 95 minus 68. Does that give me 27? Okay, so that means that 13.5% is going to be on this side, but 1 standard deviation and 2 standard deviations, and 13.5% is going to be on this side. Also. Okay, and so then it goes from 5 to 99.7. So there's going to be 2.35% there and 2.35% there. And then above 3 standard deviations, there's 99.7 within 3. So let me curve. So that's going to be 0.5%. And below is also going to be 0.15%. So for example, let's say that you take the SAT. And we know that the SAT is normally distributed with a mean of 500 and a standard deviation of 100. And you're very bright in math, right? So you score, let's say, there's one little question that trips you up. Let's say you score 790 on the math, okay? So you're just below 3 standard deviations above the mean, right? But that means you're going to be at an extremely high percentile in relation to everybody else who took the exam. Probably 9 percentile, maybe 98, right? But probably very high. All right, so this says, using the sketch above, what percentage of 12-year-old boys will be over 157 centimeters tall? So that's asking what above 1 standard deviation. So we have 13.5% plus 2.35% plus 0.15%, adding those together. That means about of the population of all will be greater than 157. What percentage of 12-year-old boys will be between 1/3? Okay. Calculated the percentages there. That's between 2 standard deviations, which gives me 13. All right. Suppose that a distribution of test scores is approximately normal and the middle 95% of the score 84. What are the mean? Okay. There's mu. Right, so 90, 70. So then that is 2 standard deviation from negative. So if this is 72, or from 72 to 84, and there's 4 standard deviations. 1 is 3. Okay. And this is 81. A normal distribution. 8 equal to 3. Okay, let me stop right there for a second. Any questions so far? Standard normal distribution, okay? Normal distribution, it always has a mean of 0 and a standard. So what we're doing when we are finding standard normal distribution, standardizing the score. So this says the proportion of observations from the standard normal distribution that are okay. A quick little sketch here. So I've got right there. Less than 0.54. So let me introduce you to your new best stats friend, Norm. Okay. So it looks like this. We write down normal CDF. It stands for cumulative distribution function. I'm going from negative infinity to 0.54. And then mu and sigma are 0 and 1. Okay, so this is the lower bound. This is the upper bound. This is mu and sigma. And it's always in that order. Lower bound, upper bound, mu, and sigma. And if I'm finding a z-score, this is all 0 and 1. So let me show you how something is there. I'm going to calculate and use CDF. All right, so let's go to our calculator. Give me 1 second. Okay. Okay, so go to Flashpad, which is between escape and tab. Hit menu. And then go to statistics. And from statistics, go to distribution. And then I want option number 2, which is normal CDF. The lower bound default should be negative infinity. So leave that as it is.
How do you hypothetical? Where was it?
Okay. Hold on, and I'll show you in just a second. Okay. The upper bound, I'm going to put in 0.54. And then 0 and 1 are going to be mu and sigma. And so I'm going to hit OK, and it gives me 0.705. To infinity, hit Control, the blue button, and then the book right there below delete. And it should give you a list of characters, one of them being infinity. So you got to put in the negative sign next to the enter there. I do. I will show you in a second. Okay. Okay, so 1 second here. Let me go ahead and do the second one. All right, while I'm here, and then we'll go back to the notes and fill that in. Okay, so the second one says greater than negative 1.12. So that means my lower bound 1.12, my infinity, mu and sigma 0 and 1. So let me go through the steps again. Okay, so watch. I'm going to go to menu, stats, distributions, normal CDF, which is option 2. Okay, so this time I need negative 1.12. So negative 1.12. Make sure you put in the negative sign there. That's important. Okay, my upper bound, I need positive infinity. So look up here for a second. To get the infinite symbol, I'm going to hit Control, and then the book, the little book, which below the delete, And when you do that, all of these symbols should pop up, and I'm gonna click on infinity there. And then click OK. So I see that this proportion is 0.869. So let me go back to the notes here for just a second. And fill those in. Okay. So this was 0.705. This is normal CDF, negative 1.12, positive infinity, 0 and 1. And this was 8.69. So a couple of things. You should always get a decimal here when you're doing normal CDF. Okay. And the reason is because the total area under the normal distribution is what?
One.
The total area is always 1. Okay, so if I'm finding a proportion of observations, it should be a decimal. Okay. So here's what I want you to do. I want you to do C, D, and E for me with your calculator. Do that for me. The notation, you can also do these on the 84 or 85, but you have to put infinity in differently. So it looks like this. It's normal CDF, negative 1 e to the 99, positive 1 e to the 99, 0 and 1. So this is negative infinity and this is positive infinity. And to get, you gotta get to distributions with bars. Second variable, and then normal CDF should pop up, and then put in infinity with negative 1
I found it in catalog.
e to the 99. Either way is fine. Okay.
Quick question, do we need to be writing normal CDF parentheses equals that for each question?
You do. You need to write out normal CDF every time. Okay. So yes, I understand that this is all calculator work. You need to show work. Okay. So write out normal CDF, put in the lower bound, upper bound, mu and sigma, and then the answer. Yes.
So you distinguish what the use first, or is it's less than
Okay. So
30?
since this is less than 0.54, I'm going from negative infinity up to 0.54. Since this is greater than negative 1.12, I need negative 1.12 is going to be my lower bound. And since it's greater than, positive infinity will be my upper bound.
Okay, so if it's less than, it'll always be negative infinity?
Not always, because if it's less than just a certain value, then yes, that's correct. But that's not, negative infinity is not always going to be your lower bound. Does that
Oh,
make sense? Mhm. Check your answers there with your neighbor. So normal CDF, 3.89, positive infinity, 0.1. Okay. So check with mine. This should be 0.00005, 0.278, and 0.866, okay? And you should always think about these answers in context, right? Answer makes sense. Well, if it's almost 4 standard deviations above the mean in a normal distribution, then yes, this proportion is going to be very, very small. Okay, and if it's between 1.5 standard deviations, that'd be somewhere between, according to the empirical rule, somewhere between 68 and 95%. Right? Yes.
Did you ever change?
Not if it's the standard normal distribution. Okay, so in other words, if you're finding a z-score, mu and sigma are always going to be 0 and 1. All right, so let's look at the next page here. A little bit more. I'm gonna stop and hand back your quizzes from Friday. So in the 2008 Wimbledon tennis tournament, Rafael Nadal averaged 115 miles per hour on his first serve. Assume that the distribution of his first serves is normal. So we got a normal distribution with a mean of 115, standard deviation of 6. That's mu and that's sigma. So part A says, about what proportion of his first serves would you expect to be slower than 103 miles per hour? Okay, so students miss points often for being lazy. So don't be lazy. All right. I want you to write down all of this process and get all the points for stuff that you know how to do. Okay, so I want to find a portion that x is less than 103. So I need to find a z-score. So my z-score is always going to be x minus mu all over sigma. Okay, so let me go back right here on the previous page. We have a z-score, x minus mu or sigma. All right, so I'm going to 103 minus the mean, which is 115. And standard deviation was 6. Okay, so that gives me negative 12 divided by 6. So my z-score is going to be negative 2. So I want the proportions of z-scores that are less than negative 2. So now, once I find the z-score, that into normal CDF. Okay, so we go normal CDF. My lower is going to be negative infinity. I want everything less than 103 or negative 2. My upper bound's negative 2. Mu and sigma are 0 and 1. So now take your calculator and find normal CDF from negative infinity to negative 2. And somebody help me out with that answer. Okay, so 0.023. So to answer the question, I'm going to say about 2% are slower than 103 miles per hour. All right, about what proportion of its first serves would you expect to exceed 20 miles per hour? So I want the proportion that x is greater than 120. All right, so I need to find a z-score. It's going to be 120 minus 15 over 6. which gives me, let's see, 5/6, which is 0.833. So proportion scores 833. So I'm going to take that and make that my lower bound for CDF. So normal CDF 833 positive infinity 0, 1. Kind of ran out of room there. So take your calculator and put that into normal CDF. And somebody help me out. What'd you get? 0.202. So I'm going to say about 20% will exceed 120 miles per hour. And then the last here on this part, it says 1% of Rafael Nadal's first serves are between 1 and 110. So I need to find two z-scores this time, one associated with 100 and one associated with 110. So I want the probability that X is between 100 and 120. Thank you. All right. So I need the z-score for 100, which is 100 minus 15 over 6. That's going to give me negative 15 divided by 6, which is negative 2.5. And then my other z-score, 110. That's 115 over 6. And that should be negative 0.833. Okay. And so last thing here, normal stuff from my lower bound at negative 2.5, my upper bound at negative 0.833, 0 and 1. Make sure you put in negative. And somebody help me out. Percentage. Okay. About or between or okay, so let me do one more thing here, and then we'll finish for the day. It says Nadal serves what's given percent backwards. So this is some. So this time I'm going work backward. Let me later here. And whenever working, need a new distributions. Put it in 3. And the area, listen closely, okay? The area is always every to the left. Okay, so I'm not going to put in 30%. I'm going to put in 0.7 because that is the area to the left. Mu and sigma are still 0 and 1. So I'm going to hit K, 0.524 there. Let me go back. Let me go back to the notes. Okay, so this is inverse norm. The area is 0.7 because the area to the left of 30%, mu and sigma are 0 and 1.
Was the left, just the area not included? Yeah, it's like if we had the bottom 20%, just the lowest 20%, would it be the 80% to the right?
No. It's always to the left.
It's always,
If they said the bottom 20%, then you would do inverse norm of 0.2. Okay. All right, so this value was 0.524. Okay, and so this, look up here, this is a z-score. Inverse norm is where we work backward percentage to get a z-score. So I need to set up an equation here. I've got my z-score, 0.524 equals something minus 115 over 6. So put in mu and sigma. And then solve this algebraically for x, okay? So I'm going to multiply by 6 on both sides and then add 115. All right, and if you do that, I got 118.146. 146.
1.44. Or sorry,
118.144. Okay. Was it?
Wow.
At that, it's close enough on that. All right. All right. So normal CDF, we find z-scores, upper bound and lower bound. If they give us a percentage, we're going to use inverse normal to work backwards there. And I'm going to stop there for the day.